I'm going to talk about extrema for functions of two variables. And first I'm going to, much like how we started our discussion of extrema in the single variable calculus class, I'm going to start with, definition of a critical point. Okay, critical points are places where we could potentially have an extremum, but not guaranteed. Right? So a critical point in AP calculus was a place where the derivative was either 0 or undefined. But we don't really have the derivative right now, so what are we going to do? So we say that z equals f of x and y has what we would call a critical point when either the gradient is 0 or one of the partials is undefined. Okay, one of the partials being undefined would cause the gradient to not be defined, but it's kind of more specific for us to say that one of the partials is undefined. So when gradient of f is equal to the 0 vector, which I guess for anybody that didn't take linear algebra with me last semester, that's the vector 0, 0. This could be true for, say w equals f of x, y, and z, or, some real valued multivariable function that maps Rn into R. We would just need more zeros. Has a critical point when either the gradient is equal to 0 or one of the partials fails to exist. Okay. So I'll start with the example that I'm going to work, and I'm going to eventually find the extrema and everything, but I haven't really told you how to do that. But I will find the critical points. So if I've got z equals 4 plus x to the 3 plus y to the 3 minus 3xy. Hold on, let me check and make sure it's the same example I worked last time. Yeah, it is minus 3xy. I had written down plus 3xy, but I'm not really sure how that would impact the problem. Okay, so the critical points of this thing, what I'm going to need is I'm going to need the gradient. I'm going to need the gradient of z, and we're going to find out if that's ever always 0. I think it's reasonable to say that, looking at this is very polynomial in x and y. There's not going to be anywhere where any partial derivative is going to fail to exist. We don't have any division by a variable. We don't have any square roots. We don't have any natural logs. We don't have any trig or any sort of issues that could cause a discontinuity in the derivative. So I'm going to say that zx is going to be 4 plus x to the 0, 3x squared, 0, and negative 3y. And then zy is going to be, 0, 0, 3y squared, minus 3x. Okay. So places where zx and zy are both 0. If x and y are both 0, that will be a critical point. Okay, so also, if x and y are both 1, I'll have 3 minus 3 for both of my partials. So that would be a situation where the gradient was 0 vector. I'll let you go in and look, do some algebra. You could pause the video if you wanted. Set both of these equal to 0, solve for one variable, substitute it on the other, find that there are no others. Okay, that's probably a good exercise for you. I know that there are no other critical points because I've worked this example before, and for the sake of the length of the video, I'm going to just not go through all that algebra. Okay, so I've got these critical points. And so now you need the second partials test, right? In AP calculus, we had the first derivative test, which was really nice because we said if the function's derivative went from positive to negative, that meant the function went from increasing to decreasing. That means we had a relative maximum. But we don't have just like this before and after. That's kind of the luxury of working on the real line, is that there is a sense of before and after, a greater than and less than. But we don't really have that in the plane, where our domain of a two-variable function. So what we're going to have to do is we're going to have to use something kind of analogous to the second derivative test, which said that if the derivative was 0 while the function was concave down, that's a relative maximum. and that if the derivative is 0 while the function was concave up, that would be a relative minimum. That's kind of the same idea of what we're doing here. Okay, so this is a theorem which I'm not going to prove here, but if you were interested in why this is true, I could definitely just ask. I could do a little bit of research and get back to you. I don't entirely recall why these two quantities that we're interested in are determining this, but if you're interested, just ask and I'll work on it. So this is the second partial test. Okay, so if your function is already at a critical point, then this holds. So if f is at a critical point, let d equal fxx fy minus fxy squared, which, if you think about it, is clearly the determinant of a 2x2 matrix. And I will say that I have seen certain explanations of multivariable concepts done with matrices, but then I got kind of spooked one time. I don't know, I told somebody something wrong, and then we had to backtrack in the class, and so I don't typically work with matrices, but I gotta point out, this is clearly, like one of those 2x2 determinants. And let this D number be that, okay? So D is gonna determine what we've got. If D is positive, then we will have an extrema. Okay, and underneath that heading, we look at the second partial of f with respect to x both times. Okay, so from here, if fxx is positive, that's a local minimum. And then if fyy is, not fyy. If fxx is negative, we are at a local maximum. If fxx was 0, then we would, well, hold on. Let's think through what would happen if that was the case. If fxx was 0, then it would not be the case that d was positive in the first place. Let you think about why that's true. Okay. If d is less than 0, if d is negative, you're at a saddle point. And a saddle point is a place that, if you kind of picture an actual saddle that you would sit in on a horse, over the horse, it looks like a maximum, right? But then there's also the thing that, like kind of supports you in the front and back. And if you think about that, that's like a minimum simultaneously as a maximum. Okay, so that's a saddle point. It is neither a maximum nor a minimum. It's kind of like in the single variable case where something was increasing, it went flat for a second, it resumed increasing at a point of inflection. But you have a saddle point. And then you may not remember because, of course, in the AP class, you don't run into those kind of like gotcha scenarios very often. But for the second derivative test, if the first derivative was 0 and the second derivative was also 0, the second derivative test was inconclusive. It didn't mean that there was necessarily not an extremum like that. Like that would definitely be a place where the first and second derivatives were 0, provided the curve that I'm kind of doing that was sufficiently smooth. But think about the graph of y equals x to the fourth. Okay, you know what that looks like. It's kind of like a parabola, except it's a little like wider at the bottom. Y equals x to the fourth. It definitely has a 0 second derivative at the origin. Yet it also has a relative minimum. Okay, so 0 second derivative doesn't necessarily mean that we can't have an extremum. Okay, but it is inconclusive in terms of the second derivative test. So if d is equal to 0, inconclusive. right, so what I'm going to do is I'm going to examine these critical points for, whether or not they are a relative maxima, minima, saddle point, or inconclusive. And what I'm going to do, I'm going to need more partials here, right? I only have zx and zy. I'm going to need zxx, zyy, and zxy. Okay, so zxx, I take the derivative of this thing with respect to x, that's 6x. Zyy, I'm going to take the derivative of this thing with respect to y, that will be 6y. And then the mixed partial zxy is going to be, okay, take the derivative of this with respect to y is -3. And notice that if you take the derivative of y, if you take the derivative of the derivative with respect to y with respect to x, you will end up with the same thing. And that's Clairaut's theorem, and that is not something I'm going to prove for you in this course because it's just heavily algebraic, it takes a long time, and it's not really very enlightening as to why the mixed partials are equal. Okay. So I've got my second order partials, which is really all I need, right? I need fxx, fyy, and fxy. So I'm just going to go in here, and let's just talk about the point 0, 0. Okay, this d number is going to be, okay, fxx is going to be 0, 0, minus 9. So d equals -9. I kind of take a step back. If d is negative, I'm at a saddle point. Okay. All right, so at the point where x is 1 and y is 1, I'm going to kind of do the same thing. Fxx is going to be 6. Fyy is going to be also 6, so that'll be 36 minus fxy squared is going to be 9. And that's a positive number. So I know I have an extremum. Now, I need to go over to fxx, and at the point I'm interested in, fxx is 6, which is a positive number. So if I have a positive number, I'm at a local minimum. Okay, so this is the type of thing that, I wish that I had the drawing skills to draw you a picture of this, but in the absence of that, we've got technology that can do it really well. So what I would recommend is going to Google, running 3D Grapher, using the first one that comes up, and just kind of, for me, the first one that comes up is a pretty nice 3D Grapher that you can kind of click on and rotate and stuff and look at. And in class, we found that really useful. We graphed z equals 4 plus x to the 3 plus y to the 3 minus 3xy, and we kind of looked around at it. At 0, there was clearly a place where you could sit in it like you were riding a horse. And at 1, 1, it was really nice. There was this kind of like part of the surface that had dipped down and hit a really nice relative minimum. Okay. So if you can look at the graph of these, it would help. It would confirm what we mean by saddle point, local minimum, all this calculation. Now, I think I'm going to come back and record a separate video on finding absolute extrema. You remember in the single variable class, what we did was we found all the critical points, evaluated the function at all the critical points, and then we also considered the end points, the boundary of our domain for a closed interval. For a function of two variables, it's going to be a region in the plane. It'll be a closed region in the plane. And so what we would have to do is we would have to check all of the points on the boundary. And that can be a little troublesome algebraically. I need to go and get myself a good example for this before I go and work it through for you. But that's something I will do in a separate video. And then kind of the nice thing is, once you do that a couple times, the absolute extrema, there's a technique, the technique with Lagrange multipliers, which makes that so much easier. Okay, so stay tuned for that. But that's all I got for this video.